Hello, my name is Özgür Kılıç and I will be presenting Rapid Memory Footprint Access Diagnostics. This is a collaborative work with Nathan Talent and Ryan Freezy from the Pacific Northwest Nation Lab. Data locality is one of the most important factors in program performance. Poor locality can cause memory bottleneck, which will affect the performance of the application. Footprint, which is the unique data items program accesses, enables the important locality and capacity analysis, but just footprint itself cannot explain the key performance issues. Let's look at the example below. In example 1, A and B, the footprint and the reuse distance between the first and the second function invocations are identical. However, the different access patterns between an array and a linked list results in different cost for the fill time due to the different spatial locality. The former example's strided references can be prefetched so that the memory latency is overlapped with the computation. In contrast, the latter's irregular pointer chasing results in exposed memory latency. In example 2, the footprint access patterns are needed to explain the performance. The footprint of A grows at the fastest possible rate, one element per load. In contrast, the footprint of L grows at a slower rate. There is a reuse for A. But the performance cost of L is far more significant due to the access pattern. Considering the example 3, depending on the data layout of the lists L and L2, their respective footprint may grow rapidly and incur significant memory cost, or they may grow slowly and benefit from the caching. We introduced new footprint diagnostics that separates the footprint into the prefetchable and irregular access components, showing that the latter is more important target for the optimization than the former. Current methods to capture footprint causes integer factor of slowdown due to the usage of the software tracing tools, which limits the use of these current tools on real application. Our motivation is to provide a lightweighted tool to calculate the footprint with access pattern diagnostics. In here, you are seeing an overview of our application. We diagnosed footprint access patterns such as constant, strided, or irregular, and the growth rate. We are using two methods, whole program and the precise method. The figure below shows the overview of our analysis. The whole program method, which is the top line of the figure, uses a memory hit profile collected with the common performance counters to infer the upper bound of the footprint access diagnostics. This method is inter-procedural and provides sufficient diagnostics within the 10% error to differentiate the access patterns and the growth rate. The additional precise step on the bottom refines the upper bound using the static binary dependency analysis and control flow profile. This method is intra-procedural and calculates the loop and the procedure footprint within the 5 to 10% error and the access patterns within the 1 to 5% error. Our techniques use a light-weighted measurement and the static binary analysis, which reduce the overhead from the factor of 200 to the less than 10%. Let's look at an example how we can use our diagnostics. We first look at context tree, and we sorted those scopes by time to find the hot path from the time. Then we focus on an interesting function. In that interesting function, we first look at the total footprint, and we divided the total footprint to the two fractions. The fraction 1 on the top is the footprint that can be prefetchable. And the fraction 2 on the bottom, that is non-prefetchable footprint. That fraction of footprint grows as irregular or non-strided. This part is more important to focus because it causes more overhead, as we talked before. That's why we zoom into this part and we look at the rates. First, we look at the footprint growth rate, which is the average unique data accesses per load for irregular accesses. Then we look at the fraction of the footprint growth due to the irregular accesses. Both of these help us to pinpoint a memory bottleneck so we can solve the issues. Let's look at our analysis in more detail. Here, we show how we bound the footprint diagnostics with the memory hit profile. First of all, there are some issues with the performance counters. They are difficult to use. For example, L1 hits include the prefetched memory. Another thing, some of the hits should count as a line, like prefetch hits, and some of them should count as a word, like the loads. Using simultaneous equation and the invariants and bounds, we can close most of the gaps. Let's look at the example on the left hand. We have two levels of the memory in this example. The first level of the memory has only 4 slots for words, and the second level has more than enough slots capacity. By looking at the hits that we could collect, we can see that there is 150 hits to the level 1 and there's 50 hits to the memory, which totals 200 hits. Without using any equation or invariants or bounds, we should calculate the footprint as 200. But with using the bounds, we should bound the footprint of the level 1 to the 4, since that is the capacity of that cache. And we should bound the footprint of the memory to the 50, since that's the total number of bits, which is smaller than the capacity. And the total footprint will be bound to the 54 instead of 200. That is way less than the 200. On the bottom, you see our equations to calculate the footprint diagnostics. By using the collected data on the right hand and the word per line calculations on the bottom of that right hand, we can create a memory hit profile from the messy performance counters, and we can calculate the footprint for prefetchable and non-prefetchable. We are using the word per line. We are calculating word per line because, like I mentioned before, the lines versus words can be different for each hit. After we collect our data and calculate the upper bound of the footprint, we use static analysis to refine the footprint bounds. We do classify the loads in the 3 categories: strided, which are related to the loop induction variable, and it increases the footprint per instance, per unique instance, by 1 word, and they are prefetchable. Frame and constant, which are the frame scalars or constant, and it doesn't increase the footprint. It only has 1 word footprint over all the instances. And the rest of them we count as indirect. This may or may not increase the footprint, that we cannot know. Let's look at the example below. By only looking at the memory hits, which is the red ones in here, we should calculate the footprint of the 4th load, the index I load, as n times m word. But with the addition of the reuse classes coming from the static analysis and the execution frequencies coming from the safety profile, we can calculate the real footprint is m divided by 2 words. Why it is m divided by 2 words? Because by knowing the load classification in here, that's a strided with the stride plus 2, we can say that, okay, this is strident with the plus 2, and it is depending to the I. That means it is m divided by 2 times getting invoked. Also, we know that it is independent from the j. That means the n is just a reuse factor. To evaluate our footprint analysis, specifically the precise method, we focused on the loop level footprint. We validate our method with using different access patterns, strided and unpredictable, different reuses, repeated or varying based on some invariants, and different sparsity of the all words in the cache or some of them. Our error rates are within the 1% for the strided and 5 to 10% for the unpredictable loads, and overheads is under 10%. In here, you are seeing the benchmark that we use to do these checks. We categorize our benchmarks in the 2 categories, strided category and the unpredictable or indirect category. Strided category uses to stress test the ability to synthesize the data from the memory hits, reuse classes, dependencies, and execution frequencies. The indirect category uses to stress test the memory hit inference rules because the indirect access severely limits the use of the correction from the dependency analysis. We use 3 different benchmark suites. The first benchmark suites in the blue boxes in here are micro benchmarks, which use to test corner cases. The brown benchmark suites, the 3 benchmarks that we use, the pull benchmark suites, and the black box in here, we use the minivite. That's a mini application for distributed parallel graph clustering, which is a real-time application that we used. And you can see the different data elements, access pattern, use frequency, and the footprint in this table. Let's look at the results. In here, we divided our results into also the same 2 categories, strided and indirect. And in the x-axis, you see the benchmarks. In the y-axis, you see the ratio to the expected. Let's first look at the gray bar in here. It is the ratio of the footprint of the our precise method to the expected footprint. You can see that for the strided ones, we can calculate within the 5%, and for the indirect ones, we can calculate the footprint within 5%, 10% error. More important than the calculating the footprint, we wanted to focus on the distinguishing between prefetchable and non-prefetchable footprint after we calculate. The blue and the red bars are showing these differences. In the strided access pattern group, we look at the prefetchable footprint percentage. In the indirect, we look at the non-prefetchable footprint percentages. And the blue bar is the precise method and the red bar is the whole program method. You can see all around the blue bars are 100% correct. It is because it uses the static analysis to differentiate which load is indirect or which load is strided correctly. By looking at the red bars, you can see that we do able to calculate the percentage of the prefetchable footprint within 5% error for the whole program method, and within an acceptable error for the indirect access patterns. We have 2 outliers. We have these outliers because they are suffering from the resolution problem. They both have small footprint per inner loop. Another thing that we wanted to focus in here is what is the ratio of the footprint to the loads that we collected. You see the light blue as the precise and the purple as the whole program method. And you can see that all of them under 20%. That means the memory bandwidth bit is way larger than the actual footprint. The ratio of the load to footprint for the precise method, it's between factor of the 5.5 to the 6,000. And for the whole program, again, it's between the factor of the 5.5 to the 42. That says we need inference rules and the static analysis to bound the footprint from the collected loads. We also looked what is the time overhead that we introduced, and we compare our method with the exact method that uses the pin. You can see in here, in the red box, that geometric mean of the overhead is factor of 1,700 almost for the exact method. But for our whole program method in the green box, it is less than 8%. For precise method, it is less than factor of 2.5. It is factor of 2.5 because we need to do 2 runs, one to collect the memory profile and the second to collect the CFG profile. And our static part is constant, so it doesn't change based on the runtime of the application. We do have some limitations. A limitation of our method is inferring the reuse in dynamically nested loops. For example, when a function's loop call another function in a loop, like in here. Our inference rules use dependency analysis to determine when the footprint should and should not grow. However, our dependency analysis is intra-procedural for the precise method. Thus, for dynamically nested loops, we conservatively assume the footprint should grow between the invocations, unless the user asserts otherwise. The minivite benchmark employs a dynamically nested loop where our default assumption is correct. In these cases, our methods fall back to the bounds from the memory heap profile. Another limitation that we require sufficient number of the samples from the memory heap profile. The footprint needs to be several multiplication of the largest cache size. And we also bound to the hardware number of the physical memory monitoring events. Only 4 programmable PMUs current Intel processor has, and we need 7 of them. We could use the time-based multiplexing, but it reduces the resolution. That's why we choose to do 2 runs to collect data. But we did not add this second run to the overhead because, like I say, we could use the multiplexing, and the future interprocessors will support 8 programmable PMUs, which will be more than enough to do in 1 run. Let's look at 2 examples. The first one we want to look is the Turkish PBF that models the metal powder bed fusion additive manufacturing process. It is designed for large-scale MPI and OpenMP simulation using the block structure adaptive mesh refinement and the hyper-scalable multigrid solver. In here, we sort the scopes based on the time to find the time hot path. Then we look at the non-prefetchable footprint cost. That's the high cost. We find the hyperindex in box function has really high footprint that is non-prefetchable, like 65%. And we realize it takes almost 25% of the time spent in here. And we introduce, to solve this problem, we introduce a prefetcher, software prefetcher, and run it again. You can see that we reduce the time from 243 seconds to 134 seconds, which is 45% reduced. And the overall time reduced like 10%. And you can see the non-prefetchable footprint percentage goes to 0. This shows the importance of the understanding the non-prefetchable footprint ratio. Also, another example in here that we used 3 different versions of the minivite. The first version, the V0, used unordered map that is a open hash table with the arrays and list. The V1 uses the hopscotch with default size that uses an array, and V2 uses the hopscotch custom size that uses vertex data. We did the same thing. We look at the hot call path by time, and you can see in here from the time, from V0 to V2, it reduces time by 67% from the 26 seconds to 6 seconds. But if you look at the third column, the footprint, the total footprint, we can see that while V0 has 7 GB almost footprint, V2 has 12 GB. This doesn't make sense at all. By just looking at the footprint, we cannot say why this is faster. But we need to look something more. In this case, we are looking at the non-prefetchable footprint percentages in that footprint. And you can see that non-prefetchable footprint is 17% in V0, but it's around 3% in the V2. This explains why it is faster. While the non-prefetchable footprint is less than 1% for the V1, it is a bit more slower. It is due to the extra copies that is happening because of the default size. This shows us the importance of the differentiating the footprint between the prefetchable and non-prefetchable and able to calculate it correctly. As a conclusion, we present a rapid method for the footprint to computing the loop level footprint by using the lightweighted memory heap profile. We present a whole program method that calculates the access patterns and the growth rate correctly. We show the importance of the distinguishing between the prefetchable and irregular footprint, as well as considering the footprint growth rate. We reduce the time overhead. We validate our method with using different benchmarks. We calculate the footprint within 1 to 10% error rate for the precise method, and we identify the footprint access pattern within 10% error rate for whole program method generally. And we are working on extending our methods to the IBM Power architecture. Thank you so much.